Hello, we'll continue with now earlier session. We'll be talking again about instruction set architecture, but this time with the slight more complex program. Instead of simple arithmetic, we will use the factorial calculation as our example. And this will help us to understand not only basic instructions like multiply, addition, subtraction, but also how the loop is implemented in instruction set architecture using comparisons and jumps. So let us write a C program that will calculate factorial of say 5. So let me start writing it. Emacs. So we'll use say name fact.c. Like this would be a program that we'll be writing for computing factorial. Fine. So let us start again the code by typing our details of stdio.h, then int main, then integer n equal to 5, integer fact. Let us say we are declaring this as 1. And then I'm just using a for loop for I equal to 1. Now, as we haven't declared integer I, so that's why I'm writing it here only. I less than equal to n and I plus plus. And the code that we want is like fact is equal to fact multiplied by I. So we know that factorial of n is like you are going to multiply n by n minus 1, then result would be multiplied to n minus 2 and so on till we get that subtraction to be either 0 or 1. So now here we are assuming that we are starting with 1 and then we are going to do that multiplication till it reaches to 5 because we have given value of n to be 5. So fact equal to fact multiplied by I, then a curly bracket again. So hopefully like this program what we wrote is going to compute factorial. Okay. Now once the factorial is computed, let us try to print it. Factorial of %d is %d. So here we'll write n and fact. Fine. And then you just write return 0. So add semicolon, then our code is done. Now let me break down this. What we had is we have a variable which is a local variable n. We set it to 5. We initialized fact variable as 1. There is a loop, for loop, which runs from I equal to 1 to n. Inside the loop, we are multiplying fact by I and storing the result in fact only. And finally, we are printing the factorial. Now let's save this and let us compile this code using GCC. So GCC fact dot c, okay, dash o. Suppose I am creating executable as fact only, fact. Fine. Now, as there are no errors, so let me execute this code as fact. Now we know that if we compute factorial of 5, then factorial of 5 would be 120. So now our result is quite good and it is correct. So at this stage, everything looks like normal C program. Now let's see how this program looks at instruction set architecture level. Now we'll ask GCC to generate assembly code. Right, so let us generate that assembly code. So here I will write -s and then fact. Like if you don't write it even, it will work. Fine. Now let us see like if we have code generated. Now earlier also we saw an assembly code generated. Now this would be basically whatever the .s file that got generated here. We know that it would be in x86 64 assembly instruction set or instruction set architecture. Now if I open this code, rather this .s file, okay, this is the particular code. Now we know that, like let me open another window. We know that we have a code with these content details. So we have two local variables, rather three variables, I, fact, and n. So n is equal to 5. That means your first value is here. Correct. Then like let me go back here. Yeah. So I will adjust the screens accordingly so that it would be good for us to see the same. So next is, this is your second variable that you have packed, say for example 1, and this is third, like where you are having, like either of them would be right now. We don't know whether which is fact and which is I. So we'll be getting about it after a while. Now it says that you have to jump. Now there is a, like we all earlier saw move L instruction. So the instruction that we are getting is jump. Now this jump JMP is basically an unconditional jump. So what it says, it is asking us to go to label L2. Now let us see where is L2. This is L2. It says it is picking first value, okay, and it is storing it in EX, and it is comparing that EX value with this value. Now we know in our code we had uh, I and N. This is where the comparison is. We know I equal to 1. Now, if I see among these two variables, RBP minus 12 and RBP minus 8, if I talk about these variables here, like above, like RBP minus 8, RBP minus 10, RBP minus 4, we know that I is 1. So, which one is giving among these three, like whatever are used here, RBP minus 8 and RBP minus 4. Among this, which one is 1? So, we know that if it is 4 and 8, 4 is containing 5 and 8 is containing, RBP minus 8 is containing 1. That means this is my I. Okay. And then N, when I say what is N? N is 5. And we are comparing I less than equal to N. So CMP. Correct. And it is comparing with EX. And in EX, we stored RBP minus 8. And that's what when we see here, like where the value exactly is added. Correct. So RBP minus 4 and RBP minus 8. So if I talk about RBP minus 4, comparison perspective, like if you see here, first value is added and multiplication is there at the later stage. Now we'll leave apart it. Now we have to compare two values. Now one of them, RBP minus 8 and RBP minus 4 would be 1, and other one would be 5. So if RBP minus 4, if I am considering this, then this is 5 for me. And RBP minus 8 is 1. So we are comparing this. There is a comparison instruction. So what we are comparing? We are comparing 5 and RBP minus 8 contains 1. So that's why this EX is containing 1. So we are comparing 5 and 1 together. Now if like here we wrote I less than equal to N. So similarly, like if you see whether I is less or equal to, we wrote less or equal to here. So it is saying jump less or equal to L3. Now, when it says if it is less or equal, like we know that in this code, if I is less than N, then it should execute fact equal to fact multiplied by I. And that's what. Now we are having another jump, and that jump instruction is a conditional jump here. JLE, jump if less or equal. It goes to L3. Now we know that I equal to 1 and I is not, I is definitely less than or equal to 5. So now multiplication should happen. So that multiplication is done here. So this is RBP minus 12. This is your fact. RB minus 12. RB minus 12 is 1. So this is fact equal to 1. So this 1 is given. RBP minus 8, we know. What is RBP minus 8 for us? It is 1. So 1 multiplied by 1, it will be 1. Then what it is going to do? It is going to do I plus plus. And this is what your I plus plus is. It is adding 1 into that I, RBP minus 8, which is our I. So I plus plus. Again, it will continue next. Minus 8 RBP. Again, the value would be picked, because you have now addition is done. So you are having 2. Now 2 is added into AX. 2 multiplied by what is the result that is earlier there. Correct. So now next value would be what? It is 2. Now fact is 1. Again, it is going to multiply it. And it will continue. When comparison would be there, like if it holds, suppose jump if less or equal, it holds, then it goes to L3. But suppose this condition fails. Suppose if I talk about here, if I becomes greater than N, then we know that it is not going to execute fact, but it is going to take printing. So here, if I see below, like when this condition doesn't hold, then there should be print. So this is your print statement, and it is printing the value appropriately there. This is how the code is working. Now, same code I can generate rather into 32-bit by writing -m32, and you can see that code too. This would be a bit simpler than what we saw at the other place. So this would be clear to you. EBB minus 12, 16, and 20. Like this would be your N, This would be your fact. Okay, one of them would be fact and one of them would be I. Correct? Depending upon how you see that in the below code. Correct? Fine. So this is how the code is getting translated to instruction set architecture. Now let us carefully interpret what is happening. What we saw, MoveL is moving the values into memory location by initializing fact and I. And this is what fact and I. Say for example. Okay. CMPL compares two values. Here the comparison is between what? I and N. Okay. Jump if. Now we are having jump if less or equal. Correct. So JLE means jump if less or equal. This is how the loop is exiting once I is greater than N. If the time it is less than or equal to N, then the loop would be continuing. Now we again can see that there is IML instruction. Okay. We know that IML instruction, which is integer multiplication, the main operation for factorial. Further, like we are adding here 1. Okay. With considering that I plus plus. This is your I plus plus. Okay. This I plus plus, whatever you see over here, is mapped here. Correct. That means this is kind of increment the loop counter. EBP minus 16, that is I, is your loop counter. And then we again saw another jump instruction, which is unconditional jump, JMP. Takes the program back to the loop. Okay, continuously execute. So the entire for loop in C is actually implemented using just few instructions like compare, jump, multiply, and increment, or like addition. Next, let us confirm that ISA type in this compilation. First, like what we did was we created an object file. So let me create an object file. So I will write here dash C and I will remove this dash S. Now, if I talk about say file, then my object code fact.o, then we know that it is 32-bit file. Okay, 32-bit LSB, what we saw earlier too. Now, if I remove this M32, then what it would be? Correct. So it would be 64-bit LSB relocatable. And this confirms that our program is using, in this case, for a while, because of this x86 64 instructions architecture, which is listed here. And when we use 32-bit, then it is telling us, like when we compile our code and generate object code, then this confirms that it is I32 or Intel 80386 instructions architecture. Similarly, you can have an objdump look for the file. So if I write objdump -d, then our fact.o file. Let me use less. So if we go to main, now this is our main. Okay. Now this is a 64-bit code. That's why you can see these are your initializations, 3 initializations. And then there is a jump, there's a multiplication. This is increment of that I plus plus. And this is again, this conditional jump and this is unconditional jump. So once the condition, like if condition holds, okay, if condition holds, it is going to go back to line number 23. That means here it will continue this loop. And this is the proper implementation of your for loop. And this is exactly how the processor executes the factorial program. Every multiplication, comparison, jump is explicitly written as an ISA or instruction set architecture instructions. So to summarize this session, we wrote a factorial program in C, we compiled it, we executed it to get the result. We generated the assembly code in 64-bit as well as 32-bit to observe ISA level instructions. We also saw high level constructs like for loop, which is mapping to compare conditional and unconditional jump, as well as addition or increment kind of instruction. We also confirmed instruction set architecture type using file command. Finally, we used objdump to look at the exactly what binary instructions were executed by the CPU. And this demonstrates the true meaning of ISA. It is the set of instruction that bridges the gap between high level language like C and the hardware execution inside C. So in next session, we'll talk more about say like your ARM architecture. Okay, where the code right now, our instruction set is 64-bit or 32-bit, but it is of Intel x86 architecture. So in next session, we'll be talking about ARM code. Like we'll try to generate ARM code on Ubuntu only. We may not be able to execute it, but we'll try to see just how the instruction set architecture is. Here, the instruction set architecture that you are seeing is a 32-bit or 64-bit architecture. Fine. So in the next session, we'll be talking about same code we'll try to take. Okay, what are the code that we earlier used, like addition, subtraction, multiplication, and the factorial code. Like we'll try to take both the codes. Actually, we wrote the code. We are going to make use of them directly. Okay. See you again in next session.